In this video, I'll be discussing the first lab in Physics 2212 on charged tapes. Introduction. This lab explored the behavior of charged tape, where the rapid separation of the tape from the spool or another tape surface provides the tape with a non-neutral charge, due to an excess or deficiency of electrons transferred between the tape and its contact surface. This experiment aimed to determine an approximate excess charge for the tapes by utilizing the repulsion on light-charged objects to float one tape above the other, and determine the distance at which the electric force and gravitational force for the top tape were equal in magnitude. These results were then evaluated by generating two computational models for the tapes, representing the tapes as point charges and line charges. For this experiment, the tapes were cut at a length of 21 centimeters. Since clear tape is approximately 1 gram per meter, the tape was calculated to be 0.1 grams, or 0.1 times 10 to the negative 3 kilograms. The top tape was then lowered to the distance between the tapes when the electric and gravitational forces canceled out, causing the tape to float, which was approximately 2 centimeters. Using the mass of the tape, the gravitational force was calculated to be 2.056 times 10 to the negative 3 newtons. By Newton's second law, the floating piece of tape must have a gravitational force of equal magnitude to the electric force in the opposite direction for it to float above the other tape. Reference the free body diagram on screen. From here we can solve for the charge based on two critical assumptions, that the charges of both tapes are equal and the electric field can be represented by a point charge. From this, we can simply plug in our values into the point charge formula and set it equal to the magnitude of the gravitational force and solve for charge. This gives us a charge of 9.56 nanocoulombs. Using the pen test, we can verify that the tapes are in fact positively charged since they attract to a negatively charged pen, and then we can calculate the electron deficiency by dividing the charge by the charge of the electrons, calculating an approximate amount of atoms by dividing the tape area by the atomic area, assuming that they're both 2D, and then we can then calculate the electron to atom ratio, yielding 1.47 times 10 to the negative 7. This leads us to Model 1. For the first computational model, the tapes were again represented as point charges and produced very similar results to that which was previously calculated, since they followed essentially the same process. The end result of this code can be seen on screen with the green vector representing the gravitational force and the cyan vector being the electric force. The second computational model was slightly more complicated, though it was based off starter code. This model represented the tape as a line of point charges and evaluated the electric force as a distributed charge among the point charges. As a result of this change in the model, the charge of the tape was increased to 9.85 nanocoulombs. Some potential errors are that the tape could have been deformed during the measurement of the separation distance, resulting in a different distance, and that charge dissipation to the environment could have affected the electric force, thus changing depending on when the tape was produced and when the experiment was observed. What if questions? If the electrons became positive and protons became negative, the overall physical interaction of the tapes would remain the same, as it's ultimately a matter of the magnitude and relative size of the tapes that yielded the results. Thus, tapes are still like charges and thus repel. However, the tapes would also be repelled by the negatively charged pen since they would now be negatively charged. What does it mean questions? The two computational values for Q are different because the point charge model overestimates the charge since it's all concentrated at one point, resulting in a strong electric field around the tape. However, the line charge model provides a reduced electric force since the charge is distributed over multiple point charges, resulting in a higher charge required to float the tape. Since tape is more like the line charge model is more realistic to the real value of the charge. Conclusion. In conclusion, this lab provided a good basis for experimentally determining the charge of charged bodies, and utilizing computational models to represent these observed phenomenon, as well as comparing generated computational models to determine which output values were most accurate to reality.